The topic for this video is arrays and pointers. So we have been introducing several things about pointers so far, and I've been mentioning in passing that when you have an array, for example, let's say that we have an array of characters named char, the name of the array, str in this example, corresponds to actually the address of the first element of this array. So the address of the first element of the array. So we have here a sort of equivalence between the notation, the array notation here, and the pointer notation here, okay? This equivalence is true, I would say, the vast majority of the time, but I'm going to stress in this video at least one of the subtle little difference that means that you should not always assume that wherever you want to handle an array, you should be able to declare it as a pointer or something like that, or vice versa, okay? We're going to look in detail into that. But first, let's look at the parts that are interesting, that are working by themselves without us having to do anything, right? So I'm going to write a little function here, void, I don't know, modify, again, and this time I'm going to say I want to take an array of int param. Okay, and I'm going to say here that I have this prototype int like so, and I'm going to declare an array data, an array data that contains, I don't know, 1, 2, 3, 4, 5, maybe, something like that, easy, that I'm going to call modify on data. And what I want to illustrate here, so what I'm going to do is I'm going to param index 0 equal 42. There we go, so that we don't even know the size of the array. I'm going to add it, but we don't need it, okay? And here it's going to be data of size 5, okay? So what I'm trying to do here is just set up the ground with a little function that's just going to work on one array, which size is known, and I'm going to change a little bit how I declare that parameter to show you the equivalence between arrays and pointers. So there we go, it compiles, a.out. When the function is done, well, yeah, I'm not displaying anything, so I'm going to display here a little for loop real quick for int I equals 0, I lesser than, you know what, let's make this a constant, and I'm going to use a symbolic constant because I don't use those enough in my examples. So there we go, size is 5, I'm going to use size here, I++, I'm going to printf one element at a time, separated by a space, and that's going to be data index I. And when we're done, well, we have already a backslash n here, so that should be okay. So I want to display that the array has been modified here. So let's go for it. There we go, 42, 2, 3, 4, 5. Originally it was 1, 2, 3, 4, 5, right? So it worked. All right, what are we going to do now with this? Well, notice how I declared the parameter here. This is what you expected, right? I want a function that's going to take an array of int. So I declare the parameter as an array of int. In the prototype, I say the type is array of int. And when I pass an argument, guess what? It's an array of int. And this is how it should be most of the time. However, because the name of the array is equivalent actually to a constant pointer on its first element, to be technical, I could do something like this. I could say, you know what, I want here to receive a memory address. And how do I specify a memory address? I just say a pointer. So int star param. And if I wanted to be even more specific, I would say int star const param, because I know I cannot modify that pointer. in star const parameter here. If I try to compile this, let's see what happened. It compiles without problem. If I try to run it, it runs without problem. So even if I omitted the keyword const, let's play with that. So I remove the keyword const here. What I'm doing is I'm passing, there we go, GCC a.out. I'm passing here when I call modify data, I'm passing the equivalent of the address of the first element of my array. Okay? Because this is what's happening whenever I use the name of the array, right? Automatically. Well, it's acceptable to say that I want here to receive a pointer, a parameter that is actually a pointer. Okay? A memory address can be stored in a pointer, then I can use the pointer, but oh, what am I doing here? So that's the second thing that is interesting between arrays and pointers, is that yes, the name of an array is a constant pointer on its first element, but I can use that name with a square bracket notation. Can I use a pointer with a square bracket notation? Absolutely. This is perfectly allowed. So here, what I'm doing is I'm using the name of the pointer that contains the address of the first element of an array, and I'm using the square bracket notation here, the indexing notation, to say I acknowledge that this is the address of the first one of potentially many elements in an array. I want to access the one at index 0, and I assign 42 to it. So the index notation that we have been using for arrays, we can also use it with any pointer, as long as the pointer points to the first element of the array. Does it have to be the first element of the array, actually? Well, let's see. What if here I said I'm going to pass the address of element data index 1, so the second element of the array, right? Let's see what happened. Compile, run. So that's interesting. What is the definition of an array? When I give you like a name like data, okay, we know this is a constant pointer to the first element of the array. So it's a memory address. This is where the array starts. So what's happening exactly here? I'm giving you the address of the second element of the array data. So in the context of the main function, I know that data has 5 elements, and I know that it starts at 1, 2, 3, 4, 5, okay? But if I pass to this function the address of the second element, then as far as the function modify is concerned, all it receives is an array, but the starting address of that array is starting later into the data array. So it's starting at the second element. So for this function, param index 0, param being the address of the second element of the array data, param index 0 is going to be the second element of the array data. Okay? And same thing here, if I decided to go back and forth between the pointer notation and the array notation, like so. All right. I can go here, GCC, a.out, and it's still working. Okay. So this is where we kind of blur the line between arrays and pointer on an element. Okay. If you have a pointer on an int, it could be that you have just the address of one int, but it could be also that you have the address of one int element that is just one element in an array in the middle of which it's located, okay? It could be the first element, could be the middle element, could be the last element, it doesn't matter, right? So having the address of an element allows you to not only modify that element, but also to use indexing to access elements that are potentially after it. So that can be a great source of error, right? If I give you the address of a variable of type double, and you take this address as a pointer in one of your functions, and then you start indexing, with index is value greater than 0, where I had only one double and I gave you its address, but you imagine that this is an array of double for whatever reason, and you start indexing, that's going to cause problem. You are going to technically read and write memory that is not the double variable that I gave you. So you're going to go past the end of my double variable and go read somewhere else in memory. So this is something that you need to be really careful about, okay? This is potentially dangerous. And that opens the topic of, well, when I have a memory address like this one, if I can use indexing, that means that I'm doing some form of arithmetic on the memory address. I'm saying param at index 0, and we're going to go back to our whiteboard here, param at index 0, so let's change that and call it param. So param at index 0, okay. Actually, I should not call that param. Oops. Let's make it like completely compliant with the example in the code. So the name of my array is data. Let's keep data like this. Data here as well, okay. Param is the name of my parameter. This is a pointer somewhere in memory that happens to point to the first element or the second element, depending on what I do on line 11, okay. So my point is, when you write something such as data, the name of the array, we know this is equivalent to the address of the element at index 0 in the array data. Already said that. When you write something like data index, I don't know, 2, for example, what is that equivalent to? Well, we have never asked ourselves what it was equivalent to, because that just meant, I'm going to look at the array data and look inside the array data at index 2 and find the element that's there. But if actually data corresponds to the address of the first element, when I specify the index 2, what I mean is I want to go 2 elements further past the address where the array starts, okay? This is where the array starts. This is one element. This is another element. So element index 0 is right where the array starts. Element index 1 is at 1 times the size of an element past the address. Element at index 2 is at 2 times the size of an element past an address. So this is the address of the first element, data index 0, okay, plus 2, which is the value of my index, times, and now I need to do the size, I need to talk about the size of an element of my array. So in this case, my array is declared as an int data something array 1, 2, 3, 4, 5. So the elements inside of that array are of data type int. I want the size of an int. Well, that's practical because what I wrote here in English, like the size of an int, and I made it look kind of like a function, actually exists in the C programming language. That's the size of operator. It spells exactly like that. You use it with parentheses. And it's actually a little deceiving because it looks like a function call, but in the vast majority of situations, the size of operator is something that is computed at compilation time. Okay, there is only one exception to that, which is variable length array. You are going to read about that in the reading assignment, but for the video, I'm going to focus on the general case, which is size of is evaluated at runtime. So I can write size of parentheses and the name of a data type here in between the parentheses, and it's going to tell me how many bytes in memory this data type, one element of that data type takes. So in this case here, what I said is we start at the beginning address of my array, and we add 2 times the size of one int. Here's the size of one int, let's say 4 bytes. Here's the size of another int, another 4 bytes. So my memory address, starting memory address for the array plus 8 bytes, this is the address where I can find this element here, element index 2. Okay, this one right here. All right. Well, let's continue our set of equivalents here. So when I use param index 2, well, that should be equivalent to param, because param is a variable that contains the address of the first element, plus 2 times size of int. Okay. Well, yes, but I don't want just to compute the address, right? What was implied here is that I was not only computing this address here, but I was accessing the element, and that was implied by the square bracket notation here. With a pointer, if I write param plus 2 times size of int, what I'm going to get is a memory address. This is going to be just a value, which is a memory address. What do we do when we want to actually read or write at a memory address? We dereference it, right? So param index 2, for example, when I write param index 2 equals 0, it's the same thing as writing star param plus 2 times size of int equal 0. But I need to dereference. So this is where you can tell there are subtle differences, right, between when we use arrays and when we use pointer. Yes, the name of an array is a constant pointer. But first, it's a constant pointer. It cannot be modified. For example, I cannot write things such as data equals, and a new memory address here. Okay. So it's a constant pointer, first thing, but beside being a constant pointer, you can see also that there are things that are implied when we use the name of an array, such as we are trying to access the element. So there is a dereference that is implied. When I look at it as a pointer, that dereference is actually not necessarily implicit, okay, like is the case here. So in this side here, I use the square bracket notation, the notation for arrays. The dereference is implicit. In this side here, if I want to do exactly the same thing that I do on the left side of my equivalent sign, I need to dereference the memory address that I compute. Okay, so that's it. We have like a summary on this whiteboard here. We have a summary of the equivalence between what we call the array notation and what we call the pointer arithmetic notation. And it shows you that in C, unlike many programming languages, there are few programming languages that allow you to do this kind of stuff. In C, you can manipulate memory address, you can store memory addresses in variable, and you can manipulate those variables in arithmetic expressions. For example, here, I am adding a value to a memory address. What does that mean to add a value to a memory address? Well, that means that you go and locate yourself at a memory address that is, for example, 1 int element further or 2 int element further. So you can use that to navigate through an array. Let's take an example of this. Let's change our loop here. I'm going to keep actually this version of the loop here. But what I'm going to do is I'm going to make another version of the loop where I'm going to do exactly the same thing. I'm going to display the content or the contents of my array. And I'm going to use this time pointer notation instead of and pointer arithmetic instead of the array indexing notation. So let's see what this looks like. So here I could say I want to access whatever is at the address data index 0, so that's the first element of my array, and I want to dereference that. I want to access whatever is at the address of the first element of my array, plus I times, let's use that size of operator, okay, size of an element of the array. Let's see what this does. Save this. Come here, compile. Implicit declaration of function size of, yeah, I misspelled it, of course. I said size of even. I wonder why I wrote size. Anyway. All right. Okay, so here's what's happening here. Interesting. So we have a %d here. We are trying to display an int. Okay. We are iterating size times, which is the number of elements in the array. We are displaying the 1 and the 5. So we have skipped all of those things. So here, this multiplication here, the size of int times I, is a little too big for this purpose. So we are going to modify this. Let's go here And let's just remove that size of int. So this time I'm saying address where the array starts plus I. Let's save this. Let's go here, gcc main.c, a.I. This time it's working. So what's going on here? Is my diagram wrong? Well, actually, technically the diagram is not wrong. It's just that when you write it like this, you can write that you are moving from the address where the array starts plus 2 times the size of int, and you express here a number of bytes. Okay. Well, when you write address of data index 0, so your memory address, plus I, you are going to add already I times the size of the element. Okay, so when we do pointer arithmetic like that on an array, adding the I here, adding the index value, is already understood by the compiler as what they mean is they don't want to add 1 byte, they want to add 1 times the size of the array. Same thing if we wanted to use a pointer here. So for example, int star p equal address of data index 0. Okay. If I wanted to use a pointer here, I could write a loop that is simply using p instead of the address of I. But if I write this, okay, star p plus I, let's see what it does. So I'm trying to go through all of the different notation that we can use, okay? So there is a missing printf new line here, but you can tell that the same result was obtained here, okay? We have the same content of the array being displayed on the screen, and now that I fixed that, it should be like better aligned. There we go. So whether I write address of data index 0 or I put address of data index 0 into p and then I write p plus I, the same logic apply. Okay, when you do pointer arithmetic like that, everything that you add to the pointer is going to be I times, if you add I, it's going to be I times the size of the element that you point to. So if you have a pointer on int, this is the size of an int. If you have the pointer on double, this is the size of a double. So we are not really worried about the byte level arithmetic here. The nature of the data type of the pointer, the fact that it's always a pointer on something, well, that something allows us to know exactly how big of a chunk of memory we point to. And when we add 1, well, we add automatically the size of one of those chunks. There is one other way that we can write things. So let me go back here, and then we are going to reset. Do we need to reset p? No, we don't need to reset p. P is still equal to the address of the element at index 0. So I'm just going to steal real quick this print f here, put it right there. And we are going to do one more loop. So I'm going to reuse p. And this time I want to do pointer arithmetic, but instead of saying that I add to p the index I, so p is the start of the array, and I add 0, I add 1, I add 2, I add 3, or more specifically 0 times the size of an int, 1 times the size of an int, etc. What I want to do is I want to increment p. So I want to do something like this. P equal p plus 1. So you could say, I just put the plus, the addition of one element size, outside this expression here, and I do it one at a time, and I repeat it n times, so nothing really changed, right? True enough. However, this can be further simplified into p plus equal 1, which can be further simplified into p plus plus. Okay, incrementation by 1 of a pointer. So the plus plus operator that we saw working on integer and scalar data type like long, etc., works also on pointers, which I can also write like this. But then I have to worry about the precedence of operator. Okay, do I want to dereference the result of how to say, of incrementing p, or do I want to dereference p and then increment it? So if you don't remember, consult the table of precedence of operator, or simply run your code like this, and you're going to see that you first dereference p and then you increment p. This is also here relatively clear because I use a post increment operator. Okay, so I can have like little expressions like that you're going to encounter a lot when people use pointers and pointer arithmetic, and they don't mean anything like really complicated. It's just a different way of writing the same thing again, which is we are doing pointer arithmetic, but this time I just keep adding 1 and 1 and 1 and 1 and 1 to my pointer at every iteration. So my pointer at the end of the loop is no longer pointing at the first element of the loop, it's pointing actually past the last element of the array. Okay? All right. So another thing that I want to show you real quick, and we're going back and forth between the similarities and the differences between arrays. What happened when I use my brand new operator size of, and I do things like size of data is, and I'm going to display here size of. So you notice that I'm using the %ZU format specifier, right? It's because size of returns a value of type size underscore t. We have encountered that type already. This is a type that's used to actually represent indexes in array. This is a type that is used to represent the number of elements in an array. This is a type that is also used to represent an offset in memory. Okay, so size of data is going to be also of that type. What I'm trying to do here is I'm just trying to say, okay, what happened when I ask for the size of and I pass the name of an array? Well, it tells me 20. Where is the 20 coming from? I have 5 elements in my array. Each of those elements is an int. An int on this particular machine, which is a virtual machine, actually, an int is stored as 4 bytes. So 4 times 5, 20 bytes. This is telling me that my array size is 20. So I could expect that if this works like this, and I'm going to move it to the end, actually, so that I have the pointer p available to me. So actually, I can move it here. There we go. So if this works this way, you know, I could expect that size of, keep forgetting the today. Anyway, the size of p should be actually the same thing. Well, it's not. Let's take a look. GCC a.out. The size of p is 8. Where does the 8 come from? So the 8 is telling me that p is a 64-bit pointer. It's a 64-bit long variable. 64-bit, that's 8 byte. Okay, so that's it. P is just a pointer. When I ask the size of p, even for p contains the address of an array, or the first element of an array, right? The size of p is always 64-bit, no matter what it refers to. You want an array on one double, 64-bit for the memory address. You want not an array. You want a pointer on a double, you need 64 bits for the memory address. You want a pointer on something as small as a char, you need 64 bits for the memory address. You want a pointer on an array of 1 million double, well, that's still just the address of the first element, so you just need 64 bits to store this address. So maybe I did it wrong. Maybe I should have said star p. Okay, it's not just p, but it's what p refers to that I want to measure. So size of star p, there we go. And I'm going to compile this, run it, and now it's telling me 4. Where is that coming from again? Well, p is a pointer on int. I declared it here on line 22. P is a pointer on int. So when I ask what is the size of what p refers to, the reference of p, right? It's going to tell me this is the size of an int. And I can verify this real quick by saying, show me the size of an int and let's compare it. So what is the size of an int data type? And it's going to tell me, again, the same size, 4 bytes. Let's compile, verify. There we go. The size of star p is 4 because the size of an int is 4. So at what point can I get to apply the size of operator on p and have it tell me the size of the array? Well, I can't. And that's one of the difference between also the name of an array and its conversion to a pointer, a constant pointer on the first element, is that yes, the name of an array is a constant pointer to the first element, but when you apply size of to it, the compiler is smart enough to know that you're talking about an array. When you have a pointer, when you have a memory address, the compiler has no way to know whether you are talking about just what is at this memory address, or whether you wanted to include, the 50 million different elements that are after that first element because it's part of an array. So the only way I could figure out, the size of my array in bytes in memory is if actually I knew how many elements I have and I multiplied the size of an int or the size of what is pointed by p, okay, these are equivalent things, by the number of elements. If I do that, then I'm going to get something that tells me how big the array is. But I had to add this information, which is, I know that I have 5 elements. So I'm going to take the size of star p, which is the reference to one element, the first element of the array, multiply that by size, which is 5, and I'm going to get 4 times 5, 20, which is the size of the array. Okay? So this is potentially a source of error. Okay, because like you can see in this video, we have a lot of cases where we can go back and forth between the pointer notation, the array notation. We can go back and forth between using an array and passing it to a function that's going to receive it as actually a pointer, and that works, flawlessly. And then we have some edge cases here and there where things are not as clear. Okay, there are subtle differences, for example, the size of, etc., or the ability to change, to reassign the name of an array. You cannot do that. Okay, you cannot reassign data equal a new memory address. That doesn't work. Data is not a pointer itself. Okay, it's evaluated at compilation time as being the address of the first element, like a const pointer, but it's not a pointer itself. We've seen that pointer arithmetic is possible, but we have done only one thing. We have done only addition of values to pointers. Well, we can subtract to pointers as well. Can we add an int to a pointer or a size t to a pointer? Yes. Can we subtract a size t from a pointer? Yes. That allows us to move forward and backward, for example, in an array. So this is what we used when we did this iteration here. Can we make the difference between two pointers? Yes. And that's going to give us a result of type size t as well. And that result is going to be what? The number of elements between the two addresses. Let's take an example. So I'm going to go at the end here, and I'm going to say I need 2 pointers, int star p1, and I'm going to say this is the address of data index, let's say 2. And then I'm going to declare int star p2, and I'm going to say this is the address of the element at index 3. Actually, let's do 4. There we go. And now what I want to do is I want to display printf. So first I'm going to declare size t diff for difference, and I'm going to say p2 minus p1, and then printf diff is %u again, and diff. So this is a third pointer arithmetic operation that I allow myself to try. Okay, the first was adding an int to a pointer, adding an int to a memory address, when I say an int, I mean a size t, a positive integer value, subtracting such a value from a memory address. And now number 3 is computing the difference between 2 memory addresses. And the behavior is pretty consistent. Okay, These three operations are allowed. Now, dividing a memory address by another memory address doesn't make sense. Multiplying a memory address by another memory address doesn't make sense, okay? Doing the modulo of a memory address and whatnot, all arithmetic operations do not make sense, you know, with pointers. But the three that I described in this video, yes, these are the three that make sense, that are also commonly used. So I ran my code in the background while I was chatting, and what we get here is diff is 2. Well, let's see, is that correct? So data index 2 is one element, data index 3 is the next element, data index 4 is the element after that. The difference between the two, yes, there is 2 elements between them. So the answer is not a number of bytes, the answer is a number of elements in that array. And it's not magical, the fact that we know how big the elements are in the array. It's because we have an array of int, and therefore we used a pointer on int to store the address of one of those elements. If we would have used a pointer on double, then the size of a double would have been used as a unit to consider what a +1 or a -1 mean, or what the difference between two pointers means in terms of units, right? So there we are. We have the rudiments here of pointer arithmetic. We have the equivalence between arrays and pointers, which can be subtle at some times, so be careful about that. We're going to wrap it up here for this video, and I'll see you in the next video. As usual, make sure that you practice this kind of stuff with the exercise. You're going to see that the module exercise are a little bit different than our usual apprenticeship exercise. They're going to ask you to do little manipulation like that and answer a question. So use them to make sure that you understand thoroughly those subtle difference and those equivalents, and then come see us during office hour if you have any doubt, any question, or if you just want to double check that what you have is actually correct. All right. And with this, I'll see you in the next video.